Hi students, welcome to my lectures on chemical reaction engineering. Today we are going to learn something about the concentration measurements. As you know, the concentration is nothing but moles divided by volume. During a reaction, the moles will change, okay, and there is a chance the volume also changes. Example, in a batch reactor, we can keep a fixed volume inside a batch reactor, whereas in variable volume batch reactor the volume expansions contractions happen, okay, because of which the concentration is changing because of moles, that is because of the reaction, divided by volume because of the expansions and contractions of the volume. Similarly, in continuous systems, that means in a reactor, we are talking about now non-batch reactor. That means a reactor is there, continuously the feed is coming every second into the reactor, continuously the product is going out from the reactor. In such cases, we measure the volume is now become volumetric flow rate, then the moles, right? Now not volume, moles, the number of moles per second coming into the reactor and how much number of moles that is going out of the reactor. And in general, moles are coming into the reactor is different from moles that is going out from the reactor. Why? Because depending upon the stoichiometry of the reaction. If 1 mole of A coming into the reactor, the reaction is 1 mole of A is giving 2 moles of B, that means 1 mole per second of A is coming into the reactor. Similarly, 2 moles of B is going out of the reactor. You can see the volume, because the moles are changing because of the reaction, the volume expansions contractions also happen every second. That when you talk about with respect to time, it is called continuous system. When you don't talk about the time, it's called the batch system. So that is why today we are dealing with measurement of concentrations in batch as well as in continuous systems. Let us start our imagine finally our agenda is to find out the concentrations, and the important is, let us talk about the batch systems. In batch systems, 2 categories will come. One is constant volume, that means volume of the reactor is fixed, and second is volume of the reactor can vary, okay. If you talk about the volume of first category in batch systems, it is constant volume reactors or reactions. I mean, volume will not change because it's talk about the constant volume. That means rigidly fixed the volume of the reactor. I am not allowing it to expand or contract. In such cases, because of the reaction, volume will not change. That means before the reaction and after the reaction, the volume remains the same. That is why V0 is volume before the reaction and V is volume after the reaction is constant, which is liters, okay. And you know the concentration, before that, moles. If you listen to my earlier lecture, and final moles is equal to initial moles into 1 minus x. X is the conversion. More is the conversion, more is the amount of A that is getting reacted. A is my reactant. Final moles of A because of the reaction is equal to initial moles of A into 1 minus x. X is the conversion. More is the conversion, less is the moles that is present after the reaction, because the amount of A is going to get reduced if you take A gives rise to B. If A is my reaction, A is my reactant, B is my product. Okay. Now we know the volume, we know the moles. At any point of time inside this batch reactor, if I have to measure the concentration, I need to know number of moles and volume of the reactor. I know number of moles is Na0 into 1 minus x. V is equal to V0, which is constant. That means my concentration is Na0 into 1 minus x by V0. More is the conversion, after 10% conversion, what is my concentration? After 20% conversion, what is my concentration? That means the concentration of A inside the reactor with every conversion you can able to calculate from this equation. Okay, you know Na0 by V is initial moles by initial volume is my initial concentration, that is Ca equal to Ca0 into 1 minus x. This is the famous equation you can able to remember. And and same constant constant volumes, and you can see if it is volume is varying, that means you are allowing it volume of the reactor to compress and expand, then it comes under the variable volume reactors. Let us see what the variable volume looks like. So for you, because concentration is equal to moles by volume, I know Na equal to Na naught into 1 minus x. If volume is changing, then how can I measure the change in volume? We have to take the help of a ideal gas law, or any other non-ideal equation of state is also can be used to estimate the volumes. I know before start of the reaction, and what is my pressure, what is my volume, what is my initial moles, that is moles of A, moles of B, moles of C, any, because if this is my reaction, A plus B gives rise to C plus D, and total moles I have to take before the reaction, how many moles of A, B, C, D is there, final moles of after the reaction, what is the moles of A, B, C, D, we have to know. And if you remember my earlier lecture, you can able to calculate all these factors. Okay. Before the reaction, this is my pressure, this is my volume, this is the total moles of A, B, C, D, and R is a universal gas constant, T is the initial temperature. After the reaction, because the volume changes and temperature changes, pressure changes, everything changes, then PV is equal to NTR into T. What is NT? This is P, final pressure, final volume, final total moles of A, B, C, D, R, and final temperature. If you use 2 by 1, if you divide the second equation by first equation, final volume is equal to initial volume into initial pressure by final pressure, final temperature by initial temperature, final total moles by initial total moles. And let us do this simplicity now. Today, we are discussing about isothermal system and isobaric systems. That means because of the reaction, the temperature is not changing, because of the reaction, pressure is not changing. In such cases, final temperature by initial temperature is equal to same, which is 1. Initial pressure by final pressure is equal to 1. If you plug these two here and here, these two ratios become 1. And what is my NT by NT0? Final moles, final total moles by initial total moles. I know from the previous class, final total moles is equal to initial total moles plus delta Na0 into x. You know delta is equal to stoichiometric coefficients of the products minus stoichiometric coefficients of the reactants. Na0 x is my conversion divided by NT0. From this, if you simplify, 1 plus delta Na0 by NT0 into x, that is nothing but 1 plus delta, what is A in total, that means ratio of total moles of A divided by total moles of A, B, C, D, that means fraction, that means amount of A divided by amount of A, B, C, D. If you do that, then it will become a fraction of A. Ya0 is the mole fraction of A in the total mixture before the reaction initiated. Okay. Then delta into Ya0 in the Fogler, I'm following the Scott-Fogler textbook, and that is nothing but epsilon. Okay. Then if you substitute the epsilon here, NT by NT0 is equal to 1 plus epsilon x. Now you know T by T0, you know P0 by P, you know NT by NT0, you substitute everything here, then you get V, final volume, is equal to initial volume into 1 plus epsilon x. That means now you know how my volume is changing with conversion. Okay. If epsilon is positive, final volume is greater than the initial volume. If epsilon is negative, that means final volume is less than the initial volume. Okay. Now you know how my volume is changing with respect to conversion. Now I substitute in the concentration. Concentration nothing but mole by volume. Mole is nothing but Na0 into 1 minus x. Okay. Volume is nothing but V0 into 1 plus epsilon x. Now Na0, initial mole by initial volume, is nothing but initial concentration, that is Ca, final concentration, is equal to initial concentration into 1 minus x by 1 plus epsilon x. This is how you can measure the concentrations in the variable volume scenarios. Let us do the same analogy in continuous systems. Here the volume, we are dealing with volume. In continuous systems, we deal with the volumetric flow rate. But here in continuous systems, I told you we have to take everything with respect to time. Okay. Here the no time factor is involved. That means liters. Here liter per second. Okay. Here it is moles, and here it is moles per second. Here Na is moles, here Fa is moles per second. Okay. Here nu is the volumetric flow rate, here V is the volume. This is the only difference, rest everything remains the same derivation. Finally, we are going to get that Ca equal to Ca0 into 1 minus x for the constant volume. Here also Ca equal to Ca0 into 1 minus x for the constant volume systems. And here for variable volume we get Ca equal to Ca0 into 1 minus x by 1 plus epsilon x. Here also we are going to get Ca equal to Ca0 into 1 minus x by 1 plus epsilon x. Everything remains the same, only one thing, here moles, here molar flow rate, here volume, here volumetric flow rate. Okay. Let us see how in my continuous system what is my constant volume and what is my variable volume. In constant volume, that means here there is a reactor. Okay. Nu is the amount of liters per second going into the reactor, nu is the amount of product that is coming out of the reactor in liters per second. Here both are the same, that means the mole liters per second that is going into the reactor, which is same amount that is coming out of the reactor, and it is the constant volume systems. We are not allowing the reactor to change its expansions and contractions. And the other thing is variable volume, same, that means I am allowing the things to expand and contract in the reactor. Example, some pictorial representation, V0 amount of liters per second that is going into the reactor, and V amount that is coming liters per second going out of the reactor. Both are not same because depending upon the moles. Example, A gives rise to 2 times B, that means 1 mole of A giving 2 moles of B, that means before going into the reactor 1 moles per second is going into the reactor. After the reaction 1 mole of A is giving 2 moles of it, that means 1 mole is entering, after the complete reaction 2 moles per second is coming out. You can see the volumetric flow rates are doubled here. If the other is, example, 2 moles of A is giving 1 mole of B, that means 2 moles per second is entering into reactor, after the reaction 1 mole of B is coming out of the reactor. That means you can see 2 moles per second is going in, 1 mole per second is coming out of the reactor. Because moles are changing, volume will change, because if you remember at STP conditions 1 mole of any gas occupy 22.4 liters. If suddenly 2 moles of gas is coming out, the volume is now 44 liters around. So that is why you have to this volume changes are very, very important for gas phase systems. If same reaction happens in the liquid phase systems, liquid volume will not change, okay, and liquid is incompressible. Whereas the same reaction happens in the gas phase, the volumes expansions, contractions happen, because volume of the gas easily affected by the change in moles, but same reactions happens in the liquid. As long as liquid is there, liquid phase reactions, all liquid phase reactions, you don't see any volume changes. Whatever the things we are discussing, it's very much important for the gas phase reactions. Okay, let us take constant volume, nu. That means nu 0 is the initial volumetric flow rate, nu is the final volumetric flow rate, which is constant. Okay, this is a batch system. Batch constant volume in continuous systems, and I know Fa is equal to Fa0 into 1 minus x. Similarly, moles, final moles is equal to initial moles into 1 minus x. Here final final molar flow rate is equal to initial molar flow rate into 1 minus x. The units is a moles per second. Okay, keep it in mind. Then what is my final concentration is equal to final volumetric flow rate, final molar flow rate divided by final volumetric flow rate. Molar flow rate units moles per second, volumetric flow rate units liters per second. Finally moles per liter will come. Okay, final concentration is equal to final molar flow rate divided by final volumetric flow rate. What is my final molar flow rate is nothing Fa0 into 1 minus x, and V is equal to, because here constant volume systems, final volumetric flow rate is equal to initial volumetric flow rate is equal to final volumetric flow rate. That means V can be replaced, nu can be replaced by nu 0, then Fa0 by nu 0 is equal to initial concentration. That means final concentration is equal to initial concentration into 1 minus x, which is same as that of we have got here. Okay, here we have to deal with flow rates, here we have to deal with normal liters and moles. Same, if the same system, variable volume, that means initial volumetric flow rate will not be equal to final volumetric flow rate. Those are called variable volume systems. If that kind of systems is there, how I can get the concentration? Concentration is nothing but molar flow rate by volumetric flow rate. Now V is not equal to V0, then what is V? I mean, what is nu? Okay, then let us get what is nu. Again we use ideal gas law. Here PV equal to nRT, here PV equal to FRT. P0, nu 0 is equal to FT0 RT0. Nu 0 is in volumetric flow rate, FT0 is in molar flow rate. Finally you get the units of, I mean, ideal gas law only. Okay, it is initial condition is P0 nu 0 into is equal to F0 into R into T0. Final, after the reaction, final pressure into final volumetric flow rate nu is equal to final molar flow rate into R into T, final temperature. Now 2 by 1, nu equal to nu 0 into P0 by P, T by T0, Ft by Ft0. We know currently we are dealing with isothermal systems, isobaric systems. In isothermal systems, T by T0 equal to 1, isobaric systems P0 P equal to 1. Then what is by Ft by Ft0? I know Ft equal to Ft0 into 1 plus delta into Fa0 into x. Ft0 is Ft0. Once you simplify, you get 1 plus delta into Fa0 into x by Ft0. What is Fa0 by Ft0? It is also same, fraction of A in all. That means, let us say in the reaction A, B, C, D are there. In this A, B, C, D, what is the fraction of A? That is nothing but what is the molar flow rate of A divided by total flow rate of A. Okay, only molar flow rate of A divided by total flow rate. Then you get fraction YA0, that is mole fraction of A in the total mixture. That is nothing but Ft by Ft0 is nothing but 1 plus delta into YA0 into x, in the epsilon equal to delta into YA0. Okay, then Ft by Ft0 is equal to 1 plus epsilon x. Now you know T by T0, you know P0 by P, you know Ft by Ft0, substitute in this equation. Finally you get V equal to V0 into 1 plus epsilon x, which is same. Okay, here you can see the same. Then what is my final concentration? Is nothing but final flow rate molar flow rate divided by volumetric flow rate. Fa equal to Fa0 into 1 minus x divided by V0 into 1 plus epsilon x. What is by Fa0 by V0 is nothing but Ca0. Okay, final concentration is equal to initial concentration into 1 minus x by 1 plus epsilon x. Okay, now you know how my concentration is changing in batch systems. Okay, how my concentration is changing in the continuous systems. Let us do one small example, then you can get a clarity then how we can able to deal with the systems. Thank you. Let us do a small example on what we have discussed now. Batch systems, I mean it's a constant volume and variable volume, and continuous systems, constant volume as well as variable volume. With an example, there is a reaction that happens inside the reactor, which is a constant volume in a batch reactor, constant volume systems. 2 moles of A plus 1 mole of A is giving 1 mole of C and 1 mole of T. Okay, and in such cases, what is my initial concentration and final concentration after a certain conversion, which is 50% conversion. And in this entire example, we are going to discuss about the what is my initial concentration and what is my final concentration after 50% conversion. And we know x equal to 50, and given initial moles of A is given around 100 moles and A0 is equal to 100 moles. Initial volume which is given 1 liter. Okay, if this reaction happening inside this constant volume reactor, then what is my final concentration Ca that I have to find out. I know Na equal to Na0 into 1 minus x, which is 100 into 1 minus 0.5, which is 50 moles. What is my volume? Volume, initial volume and final volumes are same for the constant volume batch reactor systems. Then Ca equal to Na by V, which is equal to Na into Na0. Na is nothing but Na0 into 1 minus x, which is 100 into 1 minus 0.5, which is 50 divided by what is the volume, which is 1 liter, that is 50 mole per liter. That means after 50% conversion, the concentration of A has been down to half. Initial concentration is 100 mole per liter and final concentration is 50 mole per liter. If this kind of reaction happens in a variable volume batch reactor systems, then Ca is equal to Na, my V final volume is equal to initial volume V0 into 1 plus epsilon x as we have decided, and Na naught into 1 minus x by V0 into 1 plus epsilon x given in this same reaction is happening, okay, and we have to know what is delta and what is epsilon. If you know these two, then we can able to calculate and what is the final volume after the reaction. I know given Ya0, that means mole fraction of A in the reactor is 0.5, that is given, and initial moles of A in the reactor is 100 moles, and conversion is equal to 50% that happened. If this is the case, what happens to my final concentration? I know delta, you know, delta is summation of stoichiometry of the products minus summation of the stoichiometry of the reactants, and A, B, C, D I know from this reaction, and C by A is equal to 1 by 2 plus 1 by 2 minus B by A is 1 by 2 plus 1, and my delta is negative. This is where we have to stop and discuss. When delta is negative means final moles are less than the initial moles, okay. Final moles are less than the initial moles. If final moles are small than initial moles, the volume will get reduced after the reaction, okay. My delta is equal to 0.5, epsilon is equal to Ya naught into delta, then Ya naught is 0.5, then delta is minus 0.5, and then my epsilon is equal to minus 0.25, and the value here is minus 0.25. My concentration is equal to moles by volume. My Na equal to Na naught into 1 minus x divided by V is equal to V0 into 1 plus epsilon x. I know initial volume is 1 liter because we have initial, because before the volume expansion takes place, the initial volume is only 1 liter, okay. Well, let us substitute every other value in this equation. We get final concentration after 50% conversion is 57 mole per liter, and here after 50% conversion constant volume batch reactor is 50 mole per liter. It is the constant here the 57, you can see same conversion in batch react, I mean in constant volume, in variable volume, the conversion is the same. For the same conversion, the final concentration is here 50, the final concentration of A is 57, which is more than the constant. Why? Because after the reaction the volume get reduced. Because of the volume get reduced, and the concentration is moles by volume. If volume reduced, the denominator value has got reduced, automatically the numerator value got increased. That is why here it is final concentration is 50 mole per liter, here the final concentration is 57 mole per liter, even though the conversion is same in both the cases. Let us go to the continuous systems. One is constant volume and one is variable volume. In continuous system, there is no kind of piston and cylinder kind of assembly will be there. It could be batch reactor, it would be CSTR, continuous turret tank reactor, packed bed reactor, plug flow reactor. These reactors will be there. So there won't be any piston cylinder assembly inside. The reason I have given the piston cylinder assembly just to understand why the volume increases and decreases. So let us do the same example. And the delta in continuous systems, the delta will decide whether we go for the constant volume or variable volume in the continuous system. Let us say delta will decide whether it is constant volume or variable volume. Let us say if this is the same reaction, the delta the same way we have calculated is negative. When the delta is negative means final volume, final moles will be less than the initial moles are bigger, final moles are smaller. That means because of the reaction the volume changes happens. That means if delta is negative or positive, the volume, delta is positive means after the reaction volume will be higher, delta is negative means after the reaction the volume will be smaller than the initial volume. If whether delta is positive or negative we get, then we have to apply variable volume formulas. If delta equal to 0, That means initial moles, 1 mole of A is giving 1 mole of B, that means there is no change in the moles, the volume will not change. If volume will not change, then we have to apply the formulas in the constant volume systems. So let us go for this reaction. Delta is negative, that means I have to use the formulas in the variable volume systems. Given Fa0 molar flow rates, because it is a continuous system, so everything is with respect to time. 100 moles per second, volumetric flow rate is 1 liter per second, the conversion is 50% and mole fraction of A is 50%, then epsilon is equal to 0.25, that is the way we have calculated here. Final concentration is equal to final molar flow rate divided by final volumetric flow rate. Final molar flow rate is Fa0 into 1 minus x, final volumetric flow rate is equal to initial volumetric flow rate into 1 plus epsilon x. I know Fa0, I know x, I know V0, I know epsilon. If I put everything in this equation, I got 57 mole per liter. That means you can see initial moles is 100 mole per liter and final mole is 57, because things got react. A has been reduced. Let us see example number 2, and let us see whether it comes under constant volume or variable volume. 1 mole of A plus 1 mole of B is 1 mole of C plus 1 mole of T. That means 2 moles of reactants, if it reacted, 2 moles of product will form. That means because of the reaction there is no additional or less moles is getting formed. 2 moles of is going into the reactor, that means 2 moles of a product is coming out, but because there is no change in volume. In such cases we have to apply the formulas of the constant. That means nu 0, that means initial volumetric flow rate into the reactor is equal to final volumetric flow rate out from the reactor. That means nu is equal to nu 0. Then we have to go for the constant volume systems. And if delta equal to 0, that means for this case I have calculated what is delta, the delta is 0. That means there is no change in moles because of the reaction. And Fa0 equal to 1000 moles, moles per second, and nu 0 initial volumetric flow rate is 1 liter per second, the conversion is 50%, then Ca is equal to Fa by nu. Fa is equal to Fa0 into 1 minus mix, final volumetric flow rate is equal to initial volumetric flow rate, then we get 50 moles per liter. Okay, I hope you understand and how to deal with the concentrations. Ultimately why it is important, let me tell you. Rate is proportional to the concentration, that is the speed at which the reaction happens depends on the concentration. If it is elementary reaction, Ra equal to Kca, the Ca is more, rate of and speed of the reaction is more. If Ca is less, rate of the reaction, the speed of the reaction will be less. So this concentration depends on whether we are dealing with the constant volume systems or variable volume systems. You can see the difference, right? In the concentration of A after the reaction will be different for whether we are dealing with the constant systems or a constant volume or variable volume systems. So that is why the speed of the reaction decided by the concentration is decided by whether we are dealing with the batch systems or variable volume systems. Then that is why it is important to know how to find the concentrations to design a reactor. I hope you have understood today. Let me meet with a new lecture. Thank you.